here with DFINITY. They will show us how ICP is reimagining the internet, as they beautifully said. Today our guest speaker is Dominic Wörner, if I pronounce it correctly. We will now welcome him on stage. He will introduce himself as well, and then we will listen to his presentation about ICP as well. Thank you guys and enjoy.
All right. Hello, everybody. Thanks for having me. I hope everyone can hear me. All right, that looks much better.
Yes, now you're a presenter as well. This is perfect.
Perfect. Okay, really sorry everybody for the inconvenience. So let me quickly make this full time. All right. So yeah, welcome everybody. My name is Dominic. I'm from the DFINITY Foundation, and I want to present on the Internet Computer Protocol, how the Internet Computer Protocol wants to reimagine the Internet. And I want to present a bit on why we want to build this Internet Computer Protocol, or why we have built this Internet Computer Protocol, how it works, what you can do with it, and then give you also a bit of a tour through the ecosystem of developers, entrepreneurs that are currently building on top of this protocol. But before, I want to give a bit background. So as I said, I'm part of the DFINITY Foundation. We are a Swiss non-profit foundation with the mission to build and grow the Internet Computer Protocol and ecosystem. The foundation has been founded in 2016. Initially, it was in Silicon Valley, but over the years, we're mainly based in Zurich, Switzerland, but still large parts of the team are globally distributed. We have about 250 people in total. I think about 150 of them are really in the office in Zurich, and it's like mostly a technical team. So we have lots of cryptographers, distributed system engineers with focus on virtual machines and formal verification. A lot of them came from Google and the close IBM Zurich Research Lab. And I'm a small part of that. I'm the lead solutions architect at DFINITY. My role and goal is mainly to support the builders in the ecosystem to build on the Internet Computer and make them successful. I'm based in Zurich. Originally, I'm from Germany, somewhere close to Heidelberg, and I studied originally theoretical physics and then came to Zurich to do a PhD in information systems. And during that time, I already came into contact with Bitcoin, which changed the trajectory of my life fundamentally. So, and after some time after the PhD at Bosch, working at a large research project around the economy of things, I joined DFINITY roughly 2 years ago. And since then, as I said, I'm helping to grow the ecosystem and make the builders successful. So I want to start a bit why we're building the Internet Computer Protocol. And one main reason is that we believe that the arc of history always ranges towards public networks. When you look back how the internet developed, originally it was an open network based on protocols, but in between you had a lot of private networks, walled gardens, AOL, CompuServe, all of those. You don't hear much of them because the protocol-based public network has won. And now we were in a similar situation, that when you look at compute and storage, most of this is happening in cloud environments. So you have AWS, you have Google Cloud, you have large centrally controlled infrastructure, and also on the application layer you have the large Googles and Metas and so on that keep a lot of state private. The mission and vision of the internet computer is that also on this layer the public network will win. And similar to the internet with the open TCP/IP protocol that connects devices and autonomous networks between each other, the goal of the internet computer is to connect privately owned node machines to a global network that enables to program directly on the internet, essentially. So I mean, as I mentioned, with that, the internet computer extends the public internet with a serverless cloud environment where you can build really autonomous services directly on the internet. These services can be unstoppable. They are secure and tamper-proof. They aren't controlled or can be shut down by a central provider. And we think eventually we can even achieve lower cost, because a lot of costs are actually like human operation costs. And if you build on autonomous software, you can save a lot of the cost. But the students blockchain group, and you might think we already have blockchain platforms out there. There is Ethereum with the vision of a world computer, and there are other even faster and cheaper chains like Solana or Avalanche. But when you look at the ecosystem, you still see that for most of the so-called decentralized applications, only a very small part is really running on those decentralized platforms. And most of it is still running on centralized architecture. And this is just because we haven't yet reached this, to speak of the analogy from the internet, of this broadband moment, that you have the throughput and low cost and ease of use and user experience to really put the whole application stack on a public network. And the vision and goal of the internet computer is exactly that built on blockchain technology, we aim to build a world computer that allows to build highly available, low-cost, smart contract-based decentralized applications. But the internet computer doesn't want to be the only blockchain in town. A major goal of the internet computer is actually, and we will see that later on, to interact with the other major blockchains platforms out there, because there is a lot of merit in the design of the other blockchain platforms. They allow far more replication and decentralization, which is very important for very highly secure digital assets. But the internet computer really wants to be this smart contract application platform that basically builds the glue between those platforms. So now, after the motivation, I want to explain a bit like what the internet computer is and how it works. As mentioned before, at the core, the internet computer protocol is powered by what we call node machines. And this is not the goal of the internet computer is not to connect like Raspberry Pis between each other. Like when you talk to people from the Bitcoin ecosystem or even from the Ethereum ecosystem, their main goal is that really everybody should be able to run a node at home. And this is provides a limit on what you can do with that machine, because a blockchain network is essentially a replicated state machine. And like the slowest machine in the system says basically how fast the whole decentralized computer can run. So in the internet computer, there is a specification for a node in the network, and these are high performance machines. And these machines are operated by independent parties in independent data centers across the world, across geographies, and very important, across different jurisdictions. You aren't allowed to run a node on a cloud. You really have bare metal machines in dedicated data centers. And these node machines are connected into subnets. Each subnet is its own blockchain. So they run a consensus protocol, and state and computation is replicated across these subnets. And the internet computer is then built out of a lot of these subnets. Currently, the internet computer consists of 37 subnets, and if more computation and more storage is needed, additional subnets can be provisioned and put into this mesh network. On these subnets, developers can deploy smart contracts. In the internet computer lingo, smart contracts are called canisters, and they are basically like software actors that run WASM modules and can and combine computation and state. And the really unique capability is that those smart contracts can communicate asynchronously via sending message between each other. So you as a developer, you don't need to care if a destination smart contract lives on the same subnet or lives on another subnet. The internet computer takes care of everything, of the routing, and so there is no inherent limitation of scaling the system out. So instead of having, for a typical blockchain, where you have basically a single process that is running, on the internet computer, you can scale out into as many processes as you want by adding additional subnets. And with this, essentially, the internet computer combines blockchain-like security and the capability of tokenization and digital assets with the cloud-like performance and scalability by providing this capability of scaling out horizontally. And you can have a look at the dashboard of the Internet Computer. There you can see the distribution of nodes worldwide. You can see a selection of the subnets. As I said, currently we have 37. They are not totally homogeneous. So there are subnets with a lower replication factor, so less nodes, and there are subnets with a higher replication factor. And this is a trade-off. When you deploy a smart contract, you can basically decide on what type of subnet you deploy your application. Some subnets have higher replication factors, so higher security. But on the other hand, they are a bit slower and they are more expensive to run your smart contract on. So currently, there are essentially between 13 and 14 nodes per subnet. And the block time of the Internet Computer, so the latency of a transaction, is about 1 second. Since recently, we also have a European subnet where, like, typically when a subnet is created, I told you before, we want to have it as globally replicated as possible, to have as much decentralization as possible. But there are use cases where it's very important that data stays in a certain legislation. And for that, there's also the possibility to create subnets where you have different parties running those node machines in different data centers, but still have it in a single overarching legislation, which could mean right now we have this European subnet where the nodes are all in European countries, but it could be also in the future useful to have, for example, a Swiss subnet or a Chinese subnet. You can still very easily interact, if allowed legally, very easily interact with the other smart contracts on other subnets, but you have the choice to leave data when legally required in a certain jurisdiction. So next, I want to talk a bit about the capabilities of the Internet Computer and its unique selling points, or I typically call it superpowers. So typically, when you interact with a dApp on a typical blockchain, you can't interact directly with the chain from your browser. So first, you typically download a front end from some centralized entity, and then you also, in most cases, need a wallet to sign all the transactions and pay gas fees. On the Internet Computer, you can also host the front end on a smart contract. And essentially, or in reality, every smart contract can answer HTTP requests directly. So you can specify an endpoint on your smart contract that directly can call by a browser. So you don't need any other tech stack. The other important part is that the Internet Computer employs what we call the reverse gas model, which means a smart contract on the IC has a gas balance, or we call those cycles. So the developer can charge their canisters like you would charge your electric vehicle with cycles, and then users can just interact with this smart contract without needing to pay any fees. This is extremely valuable to provide a Web 2-like user experience and to easily onboard new users. You still, of course, need to find a way to keep your smart contracts sustainable, and there's different ways to do that. But yeah, you can also charge users, of course, but with this architecture, you have a very easy way to onboard your users. The other part, what's built in the internet computer is that you can authenticate users with passkeys. So you might probably be aware of passkeys. They've been big recently, also in the Web 2 world. This means basically you don't need to you don't need to take care of a seed phrase or anything like that, because in your devices you typically have a secure chip where a private key is generated, and you can sign messages with this private key without this private key ever leaving your device. And the internet computer makes use of that so that you can just use your biometrics to authenticate against your device, and the device will then sign the message and sign you in. And the authentication system that is built by DFINITY, there are other authentication mechanisms on the internet computer. You also have a model that is very similar to MetaMask. There are a couple of wallets like that. But the authentication system that DFINITY has built is called Internet Identity, which makes use of this passkey-based authentication. And the other important part is when you typically interact with a public blockchain. So to trust what you receive or what you get from the chain, you would normally need to run your own node and really verify the whole blockchain to the current state and verify the state against that. Of course, nobody does that in practice. What the user typically is doing is just rely on some central party. So Infura is in the EVM ecosystem a notable party like that. So you typically just call an RPC endpoint and get a result and trust that result. On the internet computer, it works a bit different. So a lot of basis of the internet computer is around threshold cryptography. And threshold cryptography is a way how a private key or a secret can be shared, or not shared, but sharded between nodes in a network. And those shards can then be combined in a multi-party computation to sign messages. So all messages from the internet computer to the end user are signed with a private key that never really exists physically, but it's shared between the nodes. And one of the base innovations on that is that, so when you probably know about multi-sigs, where you also have different private keys between parties, and they can combine their signatures to a multi-sig. But the issue is the public key to verify this signature then changes if the composition of the network changes. And we don't want to have a system which is static, where all the nodes need to be the same. We will have like maybe rogue node providers or machines that are not available anymore and that need to be rotated out for different machines. And the cool thing about threshold cryptography and the distributed key generation and key resharing protocols is that we will have the same combined private public key pair forever and can change the composition of the network all the time. So what this means is when you in your device have a 48-bit public key, you can verify the authenticity of all the messages from the internet computer. But there are even more important features that the internet computer or the smart contracts on the internet computer provides. So what's also very important for the user experience is that on ICP, smart contracts can have domain names, and they can even be Googled by providing SEO. And for example, if you go to internetcomputer.org, this is a website that is hosted on the internet computer. Also, when you've interacted or when you developed smart contracts on other platforms, you may know that you normally, a smart contract doesn't do anything by itself. You always have to trigger it by sending a transaction to it. On the internet computer, you have features like timers, where you can schedule activities. So your smart contract can really be totally autonomous and is not required to be triggered from the outside. Based on this threshold cryptography, smart contracts also have access to unbiasable randomness, which is very important for all kinds of games, but also for NFT mints and other applications. Another very important feature is the low fee storage on the internet computer. So when you want to store a gigabyte on Ethereum, you have to pay a couple of $1 million. On ICP, you pay around $5 per gigabyte per year. But importantly, you really have to renew the storage, or like renew the cycles on the smart contracts, or have a sustainable business model around that. If your smart contracts would run out of cycles, and there are a couple of measures in place that this doesn't happen directly, but if it really runs out of cycles, then it really gets deleted and is not part of the state anymore. It's also pretty amazing that a smart contract on the internet computer can hold up to 400 gigabyte of data. This is a magnitude difference from other chains. We'll also very soon see that you also can call out to web services from smart contracts. So you aren't dependent on third-party oracles. I guess as a student blockchain association, you are aware that normally what happens on a blockchain, you typically have no access to the external world from a blockchain. And to get data into a blockchain, you always need third-party oracles that basically provide data in form of transactions. On the internet computer, as we'll see, we can turn this around and really like fetch data from the outside world, and also like do notifications and things like that. And we also have EVM support, so you can run EVM smart contracts, Solidity contracts as well on the internet computer, but I will also get to that a little bit later. So you might have asked yourself, I mentioned a lot of times that so we somehow create these subnets, and we have nodes that can be rotated out of a subnet or into other subnets. How does that work? So at its core, the internet computer is controlled by a DAO, a decentralized autonomous organization. And this DAO is called the network nervous system. And the network nervous system lives on the first subnet that is ever created. And if you hold ICP tokens, you can stake them in what's called a neuron. And depending on how much ICP you stake, how long you stake it, and the age of the neuron, so how long you have it staked already, the more weight you have in this governance system. And when you want to be a node provider on the internet computer, you basically have to create a proposal, and the community of neurons and token holders can decide if you are allowed to join the network, and can also, like currently this is a manual DAO voting process, you will decide in which subnet this new node will be onboarded. Sometime in the future, a lot more will get automated, so that the network nervous system will be much more intelligent itself, that it deploys the nodes directly to maximize decentralization. So currently, this is calculated by DFINITY and proposed to the community, to the DAO. And in the future, a lot more will be totally automated. Also, when you follow other blockchain protocols, for example, Ethereum, you have update cycles of a couple of months to years for a new software update of the blockchain system. On the internet computer, the network nervous system can roll out new replicas, so new ICP software versions automatically. So about every 1 week, there is a new update of the software, and then there are different people in the community who review this code and this software and verify that it really does what it should be. And then afterwards, it gets voted by the DAO and then completely autonomously rolled out on all nodes in specific subnets or all the subnets. So we have a very fast evaluation based on this on-chain DAO. So you don't need to so you don't need to convince every node provider to update software. The rollout can be really automated. And based on this network nervous system, there's also the service network system. So when you want to build a system on the internet computer, when you want to build a dApp on the internet computer, initially, you as the developer are typically what's called the controller of these smart contracts. So smart contracts on the internet computer are upgradable by default. So you have basically initially total control. And we've seen this on other smart contract platforms. It's really hard to have immutable systems from the beginning on. Software, in many cases, has to evolve over time. And initially, it's fine that it's fast. You have a developer who can iterate fast. But if people want to put a lot of funds into the system, then of course it needs to be decentralized. And the SNS is basically a way to give control over a complete application, including front end and everything, to a community of token holders. So there's a launch pad inside the NNS governance, where applications or application creators can make a proposal to create a launch of an SNS. And with this launch, you give out new governance tokens of this new application, and you collect funds into a treasury, and the governance system then controls the evolution of the software, and it also controls or governs these funds. So it's a very different model than the DAOs we've seen initially during IDOs in the blockchain space. You basically gave all the funds to the developers and hoped the best would happen. Now really the funds are all in this treasury that is controlled by the community. And the second thing, also the application is really controlled by the DAO. So in these systems that we're building, we think these are really the open internet services of the future, which are really completely controlled by the community, by the users, and a developer or a company can't quickly change the rules, the prices, kick you out, or anything like that. And you can also, again, look on the dashboard and see we've started with these SNSs. So this product launched sometime last year. And since then, there have been like 15 successful SNS launches with all kinds of applications, from decentralized social applications to games, to DeFi applications, to also here the gold DAO, which wants to tokenize gold and create a gold-backed stablecoin. So all kinds of different applications went through that, and many more will come. And what's interesting is when you look at DeFi Llama in the governance sections where they track all DAOs, and you look at the first page, you will see from the activity from the most active DAOs, you can see this pretty much owned by the internet computer and its ecosystem. So on the number one by far, we have the internet computer and the network nervous system. And then also on place 2, it's OpenChat. I will talk to you about that later. This was the first SNS that has been launched. And yeah, as you see, there are quite a couple more of internet computer DAOs or SNS DAOs. All right, let's talk about Web 2 integration. So as mentioned in the overview of some of the superpowers of the internet computer, so smart contracts can directly call web services without the need for oracles. And this is a very powerful feature that is used by a lot of applications. I don't have another slide here. Well, what happens here is that when a smart contract on a certain subnet calls an external API, essentially all the nodes in that subnet call this API and then create consensus on the result. And when you think about it, often this wouldn't work because you have maybe a timestamp in there or something like that, so that the results that the individual nodes get diverge a bit. So you can specify in your smart contract a transform function which normalizes the response to be sure that you get the same from all of that. And like typical applications that people are doing is, of course, we have an exchange rate canister that gets all the price information from I think from 7 or even 13 different sources. So it calls out to a lot of bank and exchange APIs, and then reaches consensus on all these different APIs, and only if all those APIs give the same result, then you will get the data in the smart contract. And so we have lending applications and stablecoin applications on 𝗖𝗍 that that use this feature to get data from outside the 𝗖𝗍. And we also, and we'll come to that later, we also have a project called Orally, which allows users to create custom oracles, basically. So you can create define from where you want to fetch data, how you want to process it, pre-process it, and then you can move the data, and we will see that later how that works. You can move that to other chains, like to other EVM chains. And so you can build a multi-chain oracle very easily on the internet computer. The basis for that is, again, chain key cryptography, so threshold cryptography. So, so on the internet computer, a smart contract can really have their own private keys. And this means a smart contract can be like an externally owned account or a wallet for all kinds of other chains. For Bitcoin, for Ethereum, for all the L2s, for the Cosmos chains, for everything. And this is what Orally allows, to use HTTPS outcalls to fetch data from somewhere and then create a transaction for a target chain and act as an oracle for the target chain. So this is a very powerful feature that is really a superpower of the internet computer, that you can create smart contracts on the internet computer that can seamlessly interact with other chains and can send messages to all other chains, and also fetch messages from other chains via these HTTP out calls. So you can call various different RPC endpoints from other chains, and so fetch state from other chains and be really the orchestration layer of the whole Web3 ecosystem. And again, as I said, the basis of that is threshold cryptography. So for the consensus of the Internet Computer Protocol, and what I mentioned, that you as a client can verify the authenticity of state and data from the Internet computer, we use what's called BLS signatures, which is a very efficient protocol for these threshold cryptography. For talking to other chains, the first thing we've implemented is threshold ECDSA. So this is it's another signature scheme that a lot of chains use, and we're currently working on adding other digital signature schemes as well. So if you know about that, EDDSA and Schnorr signatures, which then enable to integrate more chains, but also be compatible, for example, with the web public key infrastructure. So you can also build like a decentralized certificate authority and things like that as smart contracts on the Internet computer. And you see, you can like build ever more things on the Internet computer that typically were only possible on centralized servers. Now you can slowly build ever more as smart contracts. And yeah, as I mentioned, as you are in like a wallet, an account on other chains, smart contracts can transact other crypto. So you can send Bitcoin around, you can send Ethereum and ERC20 tokens around. With Bitcoin, we went a step further, actually. So with Bitcoin, we have subnets on the Internet computer that run part of the Bitcoin protocol itself. So the nodes in the subnet talk to the peer-to-peer messaging layer of the Bitcoin network and give the blocks into a smart contract on the Internet computer. And this smart contract acts a bit like a light client on Bitcoin. So it validates the proof of work. And then you essentially have the whole state of Bitcoin on the Internet computer and have this as an API to all the other smart contracts on the Internet computer. So you can get all the UTXOs and some other convenience functions to more easily work with Bitcoin via this Bitcoin canister. And this Bitcoin canister, I think, has now uses 80 gigabyte of storage. So it's like, I think, the biggest canister we have so far, but there's still like lot of room to the 400 gigabyte we currently make available. And this is like the most secure way of integrating another chain into a system by really essentially running nodes and doing the consensus verification. And based on that, we have a system called CKBTC for chain key Bitcoin. This is a twin token on the Internet computer that is controlled by smart contracts and is one-to-one pegged to Bitcoin. So you can send Bitcoin to a certain address, and where this 𝗚𝗏𝗏𝗁 minting canister listens and will then create new 𝗚𝗏𝗏𝗁. And when you want to move back to Bitcoin, you send to a specific address on the 𝗚𝗏𝗏𝗁 minter, and it will burn these 𝗚𝗏𝗏𝗁 tokens and will release the funds on Bitcoin again. And as you know, Bitcoin transaction costs are extremely high. Latency is also very high. So the block time is expected 10 minutes, and you typically should wait, depending on the size of the amount you transfer, but like the rule of thumb is waiting 6 confirmations. So you typically wait an hour for a transaction. But when you're on 𝗚𝗏𝗏𝗁, you have transaction fees of 10 satoshis, so way less than a cent, and you have these latencies on the internet computer of 1 second. So you have really a super fast payment system based on Bitcoin. And the second part is you can also plug into the growing DeFi ecosystem on the internet computer. So you can generate yield on Bitcoin by providing liquidity to certain lending pools, not lending pools, liquidity pools for swaps. So we have 𝗚𝗏𝗏𝗁, 𝗚CK-ETH pairs, for example. We've also a 𝗚KBTC-backed stablecoin, where you can also earn yield by providing liquidity to that. And the next step would also be to move via this chain key cryptography to also move 𝗚KBTC to other ecosystems. So export Bitcoin, a secure form of wrapped Bitcoin to Ethereum, to Solana, and so on and so forth. For the Ethereum integration, we also plan in the long run that there are subnets on the internet computer that really run Ethereum nodes, and you have this most secure integration. But since running Ethereum nodes is much more cumbersome than running Bitcoin nodes, this will take quite a while. And also what we see is that a lot less happens on the Ethereum main chain because it got really expensive to do stuff on the main chain. And we see a lot of layer 2s, rollups, and so on that are also EVM compatible, so Ethereum virtual machine compatible, but are essentially different systems. And instead of running nodes for all of them and integrating with all of them, I don't have a good slide for that. What we are doing is we have an EVM RPC canister that basically acts as an oracle here. So we call a lot of different independently run RPC providers of Ethereum or these layer 2 EVM chains and fetch the data from that, get consensus on that, and provide it to the smart contracts on the internet computer. And based on that, we launched last December 𝗚CK-ETH, so similar to 𝗚KBTC, this smart contract controlled twin token of ETH. And we are currently working on a system that allows to also create these twins of ERC20 tokens. This is scheduled to be released end of this quarter. And we also have now a lot of ecosystem teams who are exploring the design space of what you can do with this chain key cryptography plus HTTP out calls, and based on that, like the possibility to call other chains and get information from other chains. One pretty cool example application that DFINITY has built that you can try is the 𝗍𝗲𝗁 wallet. So it's a wallet, like a personal wallet that is compatible with the with Wallet Connect and so on, so to the standards in the EVM land, but that is completely run on the internet computer. So completely run by smart contracts on the internet computer, and it allows to authenticate with your biometric. So you don't need a seed phrase. You can have a seed phrase if you want, but you could rely totally on these secure hardware that is in your devices, and you can log into this wallet from all your devices that you have, and you don't need to download anything. And the key is controlled by the network and never physically in one place. And we call this security model network-based custody. So you can create a user experience similar to a custodial wallet where you have to trust a provider, but in this case, you only have to trust the network. So let's go a bit further into some of the ecosystem applications that people have built on the internet computer. So on internetcomputer.org/ecosystem, you can look through a lot of the ecosystem applications, not all of them, but you can get a good overview what's being built. I want to give you some cool examples. So the first one I mentioned already, and I later also want to invite you to a private channel for us if you have additional questions. So one application is OpenChat. It was this first SNS-based DAO on the internet computer. There are other DAOs. Tagger is another social media platform on the internet computer that don't use this SNS framework. This was, I think, the first real DAO-controlled full-stack dApp. But OpenChat is the first one that used this SNS scheme, and they raised $6 million in less than 6 hours. Meanwhile, those $6 million are way more because ICP appreciated quite a lot since then. And they now have a good treasury to advance the application, and a lot, I can tell you, a lot has happened already in this not even a year. And OpenChat started as this more like a Telegram-like thing, and meanwhile you can do a lot more. It goes more in the direction of Discord, and soon you will be able to do also video chats and things like that. And of course, you can send tokens, CKBTC, CKETH, and so on, and all the meme coins around you. You also have integrated the voting processes on these DAOs, so you can vote inside these chat applications. And also OpenChat is now part of a lot of other ecosystem applications, so that you can have a chat inside another application. Another interesting one that recently launched is Helix Markets. It's an order book-based exchange, so it feels very much like going to Coinbase or Kraken or something like that. But it runs on the internet computer, and it integrates, again, using chain key technology with other chains. So you can trade tokens from different chains on this decentralized exchange built on the internet computer. Another cool one is Bionic, and I wrote it wrong. It's with a Q in the end. I'm not sure if you are aware, but there was like a lot of activity around ordinals. So ordinals are pretty interesting thing. So first it started with like this guy who came up with a way how to enumerate all the satoshis in Bitcoin, and then also with a mechanism to attach metadata, to attach data to these satoshis, and this is what's called inscription. So you have NFTs or digital collectibles on the most OG chain that is out there on Bitcoin. So the most expensive digital property that is out there can now be used for NFTs and meta protocols and so on and so forth. And because we have the Bitcoin integration, you can build a very easy to use non-custodial marketplace for ordinals on the internet computer. And hopefully soon also people will build lending protocols where you can have your Bitcoin ordinal as collateral and things like that. Another cool feature here is they've came up with a system called reserved ordinals, because like inscribing on Bitcoin is very expensive and we can't do anything about it. So what they do, they first essentially mint an NFT as an NFT on Bitcoin, and at some point in time you can decide to then move to the Bitcoin main chain, basically. So you can have this reserved ordinal and you can trade it already, and at some point you can then inscribe it onto the Bitcoin chain. And Bitcoin ordinals need these Schnorr signatures to be created. This is where the internet computer currently doesn't support the threshold protocols. So you can't inscribe directly from a canister in a secure way. I've built a prototype where you can do it in an insecure way. But in a couple of months, we will have threshold Schnorr, and then you can also have this decentralized DAO-controlled inscription service, and so on and so forth on the internet computer. Next one is Juno. If you are a web developer and you know Firebase, so a system where you basically have authentication and a small database and all these things abstracted away, so a backend as a service where you only have to write front-end code to build a complete application. Juno is similar, but built on the internet computer. So you essentially have only to write some JavaScript front-end code, and you can create a fully decentralized application on the internet computer with persistent storage, authentication, and everything like that. So it's really cool to check out how fast you can build an application there. Then I mentioned this before, the smart contracts and ICP are so powerful that you can essentially run a whole EVM inside a single canister. And DFINITY, it's still in testnet, will launch in the next couple of weeks, is such a system where you really have an EVM run inside not a single, but a couple of smart contracts for some reason on the internet computer. And then you also have from an EVM environment access to Bitcoin and all these chain key crypto services that we provide. And then there are also, of course, funny experiments happening in the ecosystem. For example, 𝗏𝗏𝗏𝗏𝗏𝗏. When you go to that site, you really are backported in the 90s and have a virtual, like Windows 89 environment with a lot of applications built on the internet computer on your desktop that you can start and navigate the depths on the internet computer ecosystem from the long ago Windows 89 computer. They also have a token, of course. You can also invest into 𝗓𝗍. It's really cool to check out. So there are a lot of applications where people are trying to move what has been built in Web 2 to new versions in Web 3. But of course, there are also quite a few applications which can't be built in Web 2, and we hope to see even more of them. Like a couple of numbers, and then I'll hope I get to the end pretty fast. So the Internet Computer launched in May 2021, and just want to tell you a bit about the growth during the last year. So there are in the ecosystem open source developers. We don't know what private developers are, but we have almost 600 monthly active developers in the ecosystem. There was a 30% growth, although there was a big bear market in 2023. There are almost 6,000 open source repos, and also like the burn of cycles, so the activity on the internet computer grew by 150% in the last year. And every year there is from Electric Capital a developer report of the whole Web3 ecosystem. And there I want to share one graphic. So you read there that on average ecosystems, because of the bear market, lost 23% of their developers overall in the year. And here, right in the right upper corner, you see ICP, which actually gained 37% during that time. So really recently, a lot of activity and cool experiments are happening on the internet computer. And I invite you to join that movement and try building on the internet computer. Just very briefly on that. What's pretty cool about the internet computer, it's a WASM-based runtime, which means a lot of programming languages which you can compile to WASM can run on the internet computer. Sometimes you need a few tricks to make it work. But we have developed our own programming languages. The main designer of that is actually one of the founders and editors of the WebAssembly spec. It's called Motoko, and it's a very simple programming language, which is really built for the internet computer. But the disadvantage is it's a new language, so ChatGPT doesn't program it well yet, and there's not that much tooling around in libraries. So a lot of people program in Rust, and now ever more people also use JavaScript and TypeScript, or even Python. And this is the guy who is building the SDK to build JavaScript smart contracts. Recently shared this snippet. So he got Express and a couple of other important libraries in the Node.js ecosystem to work on the internet computer. So you can really, with a couple of lines of code, you can really deploy your decentralized web server, essentially, on the internet computer. And here are, so if you want to get started, if you want to build on the internet computer, here are a couple of important links. So, of course, the developer portal is very important. We also recently had with ENCODE Labs, currently finished a hackathon, and before that we had the Zero to Depth education series with lots of interesting videos that give you a good background of the whole tech stack of the internet computer. And we also have a very active forum and developer Discord. Yeah, and with that, like you maybe know this expression from Mark Andreessen from 𝗘𝗅𝗶𝗁𝗂, which coined the term software is eating the world. And we see this really happening. Ever more it's running like in the digital world. And we think that eventually smart contracts will eat software, and the internet computer is the perfect smart contract platform to achieve this vision. With that, thanks a lot. If you scan this QR code, I'll invite you to a private open chat group where I will be available also over the next days and so on to answer questions and get you started on the internet computer ecosystem. This will also move you through the process of creating an internet identity, which might be not the super best user experience at first, but I think you can make it through, and then you have really a cool privacy-preserving authentication method for most of the cool applications in the internet computer ecosystem. All right. Mm-hmm. Yeah, I can see them. Mm-hmm. Yeah, that's an excellent question. So I didn't dive into the tokenomics of the internet computer, but so if you are a node provider and part of the internet computer, then you get newly minted ICP. So similar as mining rewards on other chains, new ICP is created to pay the node providers. New ICP is also minted to incentivize participating in the governance. So stakers that actively participate in governance, so really vote or delegate their voting power to other neurons, they also earn newly minted ICP. And on the other side, you have to burn ICP to create cycles, which are then used to power the smart contracts. So we have this, this tokenomics, wheel happening. Newly created ICP via node provider rewards and staking rewards, and on the other hand, powering smart contracts takes ICP out of the system. And if the internet computer becomes a successful smart contract platform with many applications running on top, then we will get into a state where more ICP is burned than is created.
Then the next question is, it was about the costs of $5 for storage that you were talking about. What are the reasons for the low cost? Is it because, as opposed to ETH, ICP is not a monolithic blockchain, whereas you don't need to pay storage across all those nodes? Also, on ETH, you pay for the blockchain to be stored for an indefinite period of time. Gas with ICP, you pay weekly or daily. What else?
Mm-hmm. So the main reason is that, as you mentioned, we scale horizontally. So not every node on the internet computer is like storing all the data, but it's sharded. So on Ethereum, you replicate like all the data, all the state across all the nodes of the network. And on the internet computer, we have a smaller replication factor. So as I mentioned, typically between 13 and 40 or 50 instead of 1,000. But the difference is on Ethereum, everyone can just spin up a node and participate, right? So you have to have a measure against civil attacks where maybe one party presents to be thousands of nodes. On the internet computer, you have to go through that DAO governance, and you have to dox yourself as a node provider. So you have to be really a public entity. You have to be a business. You have to be in a real data center. So there's not, and we like the system knows like which data center, where in the world you are. So we can have this, what we call deterministic decentralization, where we can get a similar form of like decentralization and security with a much smaller number of replication. And the cost obviously scales with the number of replication.
That's clear. And I think that also answers the next question, because it says, what is the reason for being able to store large files on ICP in comparison to ETH, for example? But I think you already answered that question. So I will go to the next question. Isn't running a Bitcoin node really expensive if you look at the size of the blockchain and at the price of $5 per gigabyte per year?
So, I mean, currently at least, on the internet computer inside this Bitcoin canister, we don't store the whole blockchain. We basically take a new block and have like a couple of blocks, but then basically apply those blocks to the state and only store the state when it is very, very certain that it won't be rolled back. So like I think after 12 or even more confirmations, so like after 12 or more new blocks are there, this is like the state we keep and the rest we delete. So as I mentioned, the Bitcoin canister stores around 80 gigabyte of data. So it's like 80 times $400 per year for that the whole internet computer ecosystem can use the Bitcoin canister. And there also, the Bitcoin canister charges cost. When a smart contract wants to do certain things on the internet, on the Bitcoin canister, it charges cycles. So you have to pay to use the API. And from that, the Bitcoin canister can basically pay its runtime cost.
Clear. Then next is, I think it's also the last question. What is the main purpose ICP tries to solve from your personal perspective? Because we heard several use cases, but I think Daphne also is pointing out like what is really the main purpose that you're trying to solve.
So I would say that the main purpose is really to provide this vision of being able to build open internet services. So this is really software that is fully community controlled, fully controlled by a DAO or autonomous. And this is something that is currently not possible. You always have only a part running on chain, and a lot of the rest of the application stack is still running on centralized infrastructure, and you need to have some party there who basically is on the bill of AWS or someone else. So you can't have in many cases, it's like Uniswap, for example, pretty much is autonomous. But like most of the applications we use today can't be built completely on the public blockchains like Ethereum. And the goal is really to enable these autonomous or community-controlled and owned software.
All right, and now let's say Daphne would like to learn Motoko. What will be the best way to learn so?
Mm-hmm.
That's what she said.
Yeah, so the best way I would say is, so on our developer portal, there is a developer journey, and the developer journey is written out completely, and for some parts of it we also have the videos available, and this developer journey is pretty much focused on Motoko. So going through that journey will give you a good introduction to Motoko. But also please be aware, you don't have to learn Motoko. You can also start off with trying to build your smart contracts in JavaScript if you know that already.
Is it also possible that we share those Discord links within our community, since there were some devs that were not able to attend?
Mm-hmm. Yeah, I mean, I think I already shared the
presentation. You shared the presentation.
So and you, please share the presentation with.
Thank you. And the last question, now it really is the last one. What can we do to help the decentralization transformation amongst sharing?
I'm not sure if I understand the question really. I mean, like the last part amongst sharing, I don't really understand, but to help the decentralization transformation, is I think learn about the decentralized technologies and try to apply them. And the internet computer is one tool. It's probably not the tool for everything, but a lot of applications that formerly can only be built on centralized infrastructure can be reimagined and built as open services on the internet computer. So learn how to build on the internet computer.
I think that's a really nice sentence to finish it off. Thanks again, Dominic. If anyone has any more questions, make sure to join the open chat group. You will also receive this webinar through your email so that you can review it as well. We will share all the relevant links within the community as well. And have a nice evening, and thank you again for joining. Bye, guys. Thank you, Dominic.
Thank you, everybody. It was nice talking to you. And yeah, hope to see you around in the open chat or on the Discord or on the forum. Looking forward to help you on board. Bye-bye.
Bye.
Goodbye.